Alrighty guys, welcome to my video. I'm using a different program this time, so I'm able to upload to YouTube. Hopefully this is more reliable and everyone has access to it. A lot of people emailed me saying that they couldn't get access to Numerator. So hopefully this is a better deal. We'll find out. So I'm going to re-record 5.1. So if you already saw this video, obviously you can skip it, but bear with me guys. Okay, so 5.1. Chapter 5.1 is about polynomial functions and models. So the first thing you want to learn about in 5.1 is basically to finally understand what exactly is a polynomial. When you see a polynomial function or an equation that's a polynomial, how do you know it is? How do you figure that out? So there's different kinds of equations, obviously. The polynomial equation is any equation written in the following form. It's going to say y equals, and then afterwards, every single term is going to use the variable x. Okay, and then every variable has the exponent or the power raised always to a positive whole number power. So for example, I'm going to actually create an example. So example 1, okay, y equals, and let's just go ahead and say 3 over 5 x to the 4th power plus 3x to the 3rd power minus 2x squared. Okay, I'm really bad at coming up with numbers, I see that. Okay, here we go. So the first example I gave you guys is a perfectly valid polynomial, and I want you guys to see what's important here. What's important is that you use the same variable. Notice I always use x, and that the power, and I use a different color for highlighter, the power is always a positive whole number. Okay, I know you don't see a number there, but that's a 1, right? So it's always a positive whole number. What about the coefficients? What about the numbers, preceding the variables? Though that doesn't matter. That can be anything. It can be a fraction, it can be negative, it can be positive. That's irrelevant. What's important is that you have the same variable being used, but every time you use it, the power has to have a positive whole number. That's all that matters, okay? And if you have a polynomial, okay, let me actually show you a couple examples of what's not a polynomial. So this is a bad example, okay? Y equals 2. Here's a bad example. Let's see if you can see what the problem is. 2x squared plus square root of x minus 5. What's wrong with this one? There's nothing wrong with 2x squared. That's a good thing, right? This is not necessarily a bad issue. The issue, however, is with the middle term, the square root of x. That can be rewritten as the following, okay? The square root of x can be rewritten as x to the 1/2 power. And now there's your problem. The power is no longer a whole number. It has to be a positive whole number. So this is a bad example. This is not a polynomial. Let's do one more example. What if you saw something like this? 3x squared plus 2 over x squared. Let me change this first term, 3x to the 5th power. How's that? Minus 2x plus 1. Okay. What's wrong with this problem? Every single term has variable x, and if you notice, all the exponents seem to be positive whole numbers. But if you remember, the terms have to be written all as numerators. You can't have fractions, or at least the variable can be a fraction. So you first have to rewrite this term, the middle term there, 2 over x squared. Even though it says x is being squared as a positive number, it's technically a denominator. You can only have numerators, so we're going to have to rewrite that. So if I rewrite that, it's going to look like this. Remember the rule, when the variable is in the denominator, you can bring it up, but the exponent now turns negative. So it's going to say plus 2x to the negative 2 minus 2x plus 1. And now here's the issue. The power, it's not positive. It's a whole number, well, at least it's an integer, but it's not a positive integer. So it has to be a positive whole number in order for the function to be a polynomial. So although it's a function, it's not a polynomial function, so it's no longer valid for our purposes. Okay, so these are two bad examples. And now, what can we talk about? What can we say? What more do we need to learn about polynomials, at least in this first page? Well, you have to remember, guys, a polynomial has a leading term. The leading term is the term with the biggest power. So in this case, the term with the biggest power is actually the first one. This is written what we call in descending order, when you have the biggest term first, and then it goes down slowly, towards the constant. So the one with the biggest power is the leading term. And why they call it the leading term is because it actually defines the shape of the polynomial. It's so the entire shape is all dependent on what that exponent, the largest power, the polynomial has. So if the largest power is a 4, that's going to help you figure out what it looks like. If the largest power is a 7, again, that's going to give you an idea of what it'll look like. Okay. And what else is important? That power, that giant power, the biggest power of the polynomial is called the degree of the polynomial for the same reasons. It tells you exactly what it looks like, so that's why they call it the degree. So the degree of the polynomial is basically just the largest power that the polynomial has. So an example I gave you guys, my degree is 4. Okay? Another thing I want to point it out to you guys is that the sign of the leading term is also very important. So the sign of it, now it doesn't matter what value it has. I mean, it does, obviously. If it's a 2 or a 50, it's going to obviously make the graph a little different. But what's important is the sign of it. The sign of it, whether it's positive or negative, is actually very important. Remember, a negative number means it's going to point down, a positive is pointing up. So in the case I have here, the degree is 4, and because the coefficient is 3 over 5, it's a positive number, right? So we know it's positive. Okay, we're going to say it's a positive function as well. So we'll talk about that a little bit later, why that's important. Last thing I want to mention before we move on is that the domain of all polynomials is always, always, always all real numbers. It says it right here, and I'll just kind of highlight it. No matter what polynomial you have, no matter what the degree is, no matter what the largest power it is, it could be next to the 5th power, it could be the 100,000th power. The domain is always all real numbers. Okay. Now the last thing in this front page that they want us to learn about is something we never talked about before. We've always figured out how to find x-intercepts and y-intercepts, and that's pretty simple, right? But what we never actually discovered is there more than one kind of x-intercept? And there's 2 kinds, and I'm going to highlight them. So the first type of x-intercept, I'll put it highlighted green. These are the first kind because we notice the graph is actually crossing the x-axis at that point. So this is the location of the x-intercept, right? That dot right there. But the line is going through that dot. It's not going to, bounce or something. You'll see in a moment what I mean. Here's another example right here. This graph is going through the x-axis at that point. And the final example over here, it's going through the x-axis at that point. So that's one type of intercept behavior. Another kind of intercept behavior is the one we see here. Now the one you see here is actually interesting because the x-intercept is not actually going through, but it's bouncing off of it. So it's a turning point there, if you ever see that. So it's like it's going up, up, up until it reaches the x-axis and immediately turns around it once it touches it. That's what we call a bouncing or a touching x-intercept. I don't know why I say bouncing, but it touches the x-axis at that point. So that's very important that you have to know the 2 types of x-intercepts. And we're going to learn how to determine what kind of x-intercept the function will have based on certain information. We'll learn that in a minute. But before we do that, let's remind ourselves, just in case you forgot, how do you find the x-intercept? How do you find the locations where the graph is either going to cross the x-axis or touch the x-axis? And to do that, to find the x-intercept, it's quite simple. If you remember, it's basically what we did a million times. To find the x-intercept, you make the equation equal to 0. Okay, so let's see if I can kind of zoom in and just put like equals 0 there, and then you just solve for x. And remember, when it's like this in factored form, then you need to find the solutions by finding the 0 for each factor. Okay, what would I have to plug in here in this x minus 1? What value of x can I plug in there so that that factor is 0? You're thinking, why does it have to be 0? Because that's what x-intercept solves for when it's 0. So when you plug in 1, obviously, when you plug in 1 into this factor, you're going to get a solution of 0. So x equals 1 is the solution. How about the second factor? Again, you plug in negative 5. We talked about this in class, and you're going to get another 0. Okay? So that's the idea. Okay? Hopefully you guys remember this. So, sorry for that, guys. So in here, we're just going to remind ourselves, are we sure we remember how to find the x-intercept? So let's remind ourselves. To find the x-intercepts, I'm actually going to only do b. Okay, we've done a so many times, I'm not even going to worry about it. In case you haven't noticed when before I erased it, you had to have factored it first, and then you just solve for the zeros. So we're going to just do B. So in interest of saving time. To do B, all you have to do is, remember, step one is make the equation equal to 0, and then finally find out or solve for each factor's 0. So what would make x plus 1? What would x have to be for x plus 1 to be a 0? And the answer is -1, right? -1 plus 1 is 0. And then finally, for x minus 2, what would you plug into that expression for that factor to be a 0? And the answer is 2. So it's quite simple. That's all you got to do, just find the zeros. I want to actually think about this also backwards. And what I mean by that is, what if I told you the solutions and I ask you what was a factor that gave you that solution? So we're going to think of it backwards. And we have a homework question like this, so I want you guys to see it. Well, if we have 3 solutions, that means we used to have, before we found the solutions, we had 3 factors. Remember? Each factor has a solution. And if my solution was -4, what was the factor? What would have to be in that parentheses for that its solution to be -4? Well, let's see. What would be the equation that I would have to use that when I plug in -4, it would cancel out? So let's see. If I say x minus 4 and I plug in -4, that wouldn't cancel out. But if I say x plus 4 and then I substitute -4 in there, it would actually cancel out that factor, make it a 0. Perfect. That's it. So it's quite simple. It's like the opposite, right? So if the solution was -2, the factor was x plus 2, because -2 plus 2 is 0. And if the solution was +3, then I would actually put x minus 3, because the solution is 0 when x is 3. Alrighty. So that would be an example. Now, is this the actual equation? Well, not necessarily. Depends. We usually have to worry about a number right there. It's the coefficient of the whole entire function. But for now, we're just going to leave it like this. So let me erase the a. Alrighty. Now we're ready to talk about something very interesting. The behavior of the x-intercepts, whether it crosses or touches the x-axis, depends on the multiplicity of that factor. And if you're thinking, what's the or at least the multiplicity of the 0? So you're thinking, what's a multiplicity? A multiplicity is how many times the solution is repeated in the problem. And if you're thinking, what do you mean repeated? Let's look at example 5. Okay, I'm going to erase, we're not going to do y-intercept. We're just going to figure out x-intercepts. And we're actually going to find out what the multiplicity is. But in order to understand it, let me actually rewrite the equation. Negative x to the 3rd power, isn't that the same thing as saying x times x times x? And x minus 3 to the 2nd power, isn't that the same thing as x minus 3 times x minus 3? And then finally this x plus 2. So if I were to solve for the zeros for the problem I just did, the solutions for x to the 3rd power, what will you plug in x cubed for it to be 0? You would say 0. But technically, x to the 3rd power has 3 different repeats of the same question. So it's like me saying, oh, the answer is 0 or 0 or 0, which we don't do that. We're just going to say it's 0, right? We don't have to repeat it 3 times. But now we're going to say something differently. We're going to say that one of the solutions is 0, and the multiplicity for that 0 is going to be 3 in the case of 0, okay? So when x equals 0, the multiplicity would be 3 for that solution. Now, what about for the other solution? X equals 3 is another solution for this factor, right? X minus 3, 3 would be a solution. But technically, the 3 could have worked for either x minus 3 or x minus 3. In other words, it has the same solution repeated twice. So the multiplicity, I'm just going to put an m with a colon so that way I don't have to keep writing the whole word. The multiplicity is going to be 2. That makes sense? So it has a repeat of 2 solutions of the same answer. And then finally, x plus 2 has a solution of -2. And that multiplicity is 1. It only has one solution of -2. And that's the idea. We're just basically describing it. Now you're thinking, okay, great. What's the point of multiplicity? Why do I care? Well, I wrote here on the side, if you can see this, okay, I'll read it to you. The multiplicity of a 0 tells you whether that x-intercept either touches or crosses the x-axis at that point. If the multiplicity of a 0 is, and now here's the 2 cases, right? Case 1. If your multiplicity is even, that means it's going to touch the x-axis. That's very important. But if the multiplicity is odd, then it's going to cross the x-axis. I hope This makes sense. The way I remember which is which is I think of the basic equation y equals x squared, which I know it's a parabola. It looks like this, and it's touching the x-axis at the origin, right? X to the second power, origin, bouncing off the origin. I know that even multiplicities, like x to the second power, it's going to have a bouncing effect. And then for x cubed, I know that the cubic function looks like that. We agree? So the x-intercept here is at 0, just like x squared, but it's going through, and it's an odd multiplicity. It's x to the third power. And those little two images in my mind always remind me which is which, okay, in case I forget. So for the example one, number 5, since I'm gonna actually split like lines so we know that there's 3 problems here. For the x equals 0, the multiplicity was 3. That's an odd number, isn't it? Which means if it's an odd number, it crosses the x-axis at that value, x equals 0. For x equals 3, the multiplicity was 2, so that's an even multiplicity. So therefore, since it's an even multiplicity, it's going to touch or bounce off the x-axis at that point. And finally, x equals -2, the multiplicity is 1. That's an odd multiplicity as well, which means it's going to cross the x-axis at x equals -2. So I'm going to go ahead and do number 6, and then we'll do a little tiny sketch for number 6, and we're going to see what it can possibly look like, okay? So we know that there's 2 solutions, right? The solution is 2 for the first factor, and the multiplicity, let me just put m, we'll say the multiplicity is 2. Now, how do I know it's 2? Because the power of that factor is 2. That's simple. That's an even number, which implies it's going to touch the x-axis at that point, okay? And for the x equals -1 solution for the second factor, the power of that factor is 1, so the multiplicity of that solution is also 1. It's the same as the power, which is an odd multiplicity, which implies it's going to cross the x-axis at x equals -1. So if you had a quick little graph, I know you're supposed to find the y-intercept. We're not going to worry about that. We're going to say -1 is here, and 2 is here. These are x-intercepts, so I'm going to go and put dots on there. If I wanted to quickly find a y-intercept, I plug in 0. This is 0 minus 2 squared is 4. So it's going to be at 4, right? 1, 2, 3, 4. This is way off scale. Let me do it again. Actually, it doesn't matter. I'm just going to say this is 4. Okay? That's a y-intercept. We don't have to actually show work for that. Just wanted to, just so you guys can see where it came from. Now, the graph is going to, we'll learn later, when we learn end behavior, what it'll look like. But the graph is going to do the 2 different types of intercepts. At the -1, I'll highlight it. At this -1 right here, it's going to cross through that point. It's not going to bounce. It's going to cross through that x-intercept. So we're going to try to see if that makes any sense. We're going to go like this up towards that x-intercept. Instead of bouncing, we're not going to do that. We're just going to continue through. So we're going to go through that point. Eventually, you're going to cross the y-axis. It's going to turn around, right? And then it's going to eventually reach this point. That's another x-intercept. Now, according to the information we just did, it's going to only touch it at that value, at x equals 2. So I actually have to get this graph to turn around as soon as I hit that x-axis. And then the graph looks like that. This is a sketch. It's not perfect, guys, but you guys hopefully get the idea. All right, so turning points. Remember what the turning points are. Those are local maximums or local minimums. Basically, the graph is going up and then immediately goes down, or it goes down, immediately goes up. So here's an example. This is turning point, turning point, turning point, turning point, turning point. This one I just made, has 6 turning points, right? So turning point is just simple. It's a very simple idea, nothing crazy. Now, the question is, if I give you the equation of a polynomial, can you figure out how many possible turning points, or at least the most turning points it can potentially have? The answer is yes, it can have, we can figure that out. It's a really simple formula. The formula is right here, okay? To figure out potentially the most turning points a polynomial will have, we have to first get the degree of the polynomial, okay? And the degree of the polynomial, we'll call that degree some number n, okay? And the number of turning points is always going to be, it says right here, n minus 1 turning point. That's how many it's going to have at most. or less. It can have less. It doesn't have to have that much. Okay. So here's a quick example. Before I do example 7, I'll just make another example. Let's say it was x to the 7th power plus x to the 3rd power plus 2x minus 5, whatever. How many turning points possible does that problem have? Well, what's my degree? My degree, if you guys remember, is the largest power of the polynomial. So in this case, my degree is 7. So the number of turning points possible, or at least the max number of turning points, I put max number of turning points, is going to be 7 minus 1, or 6. That's the most it can have. It can also have less. So it can have 6, and it goes down by 2s, right? So 6 or 4 or 2, or 0, technically. That's the most it can have, 6. What about the example here, for example 7? Well, when it's factored for you, in order for you to figure out the degree, you're going to have to do a little bit extra work. You can't just look for the biggest term because it's not there, right? It's all factored neatly for you. So the way to figure out what the degree of a polynomial is in this format, you got to do something quite simple, but you got to do this. You take the power of the variable, you take the power of the factor, right? And then you're going to multiply these two numbers. You're going to go ahead and multiply 1 times 1, which is 1. So the degree value for the first factor is 1. And then you do the same thing for the other one. So 1 times 1 is also 1. And you add these degree values, and you're going to get the total degree, which in this case is 2. So the degree for this example is 2. And therefore, the max number of turning points is equal to 2 minus 1, or 1. And it goes down by 2, so it has to have 1. You can't have negative turning points. I'm going to quickly do another example to figure out what the degree is. So I'm going to put x plus 2 to the 2nd power, x minus 3 to the 3rd power, let's say, x squared minus 4 to the 2nd power. Actually, I'll leave it to the 1 power, and I'll leave it like that. So the question is, what's the degree of this polynomial? Now this is a more complicated case, and I'm not going to give you this. They're going to be always much easier, and I'll show you what I mean by complicated. But the way you do this is you get the degree for each factor and add them up. So the degree of the first factor is 1 times 2, or 2. And the degree of the second factor is 1 times 3, or 3. And the degree of the third factor is 2 times 1, or 2. A lot of people forget that this has to multiply to the power of the factor. So it's for you to figure out how much the degree of that factor is going to be. So that's what I mean by complicated. I'm not going to give you questions like that in the test or anything, but in case you do see it in any future class, remember, to get the degree of each factor, you multiply the power of the variable to the power of the factor. Now, once you do that, you add these degrees, and then you're going to get the total degree, right? So 2 plus 3 is 5, plus 2 more is 7. So the degree for this case is 7, which means the max number of turning points is equal to 7 minus 1, or 6. So it's quite simple, okay? Now, we're going to do one final concept before we do more examples, and this is concept about end behavior. Now, to understand end behavior, I want to give you like a little diagram, okay? End behavior is basically trying to give you an idea of what the graph will look like from far away. That's how I like to interpret it. If you were to zoom out and you ask, what does it look like? Basically, you zoom in, you see a lot of details, but zoom out and everything pretty much has a lot of similarities, right? Well, this is at least true for polynomials. Polynomials have two basic shapes, okay? So we'll start with the shapes. Let me just do like a little diagram. We're going to do, and yes, we're going to have 4 boxes, and I'll explain why in a moment, but we're just going to do for now basic shape number 1. That's a parabola, isn't it? That's pretty much what polynomials will look like if it's what we call an even polynomial. And what I mean by even, I mean if the degree is even, it's going to basically look like a parabola from far away. Now, would it look exactly like a parabola? No. I mean, like, look, let me just show you what I mean. It can look like this. You know what I mean? But from far away, you look at that and you're like, it's a parabola, So it's not exactly a parabola, but the point is, it's a parabola in a sense, right? It has both directions and left and right sides going up. Well, I'll give you further details. And if the degree is odd, it's going to be cubic, essentially. Now, cubic means that the graph is like on the right side going up and the left side is going down, right? So it's like kind of like from left to right, leaning towards up the sky, right? So that's basically the two pictures overall. Is it going to be exactly like a cubic function? No, but I mean, what I mean is it's going to look like that from far away, more or less. Now, these are what we call even odd functions if they're positive, if the leading term is a positive leading term. So if it's basically, for example, x squared, it's going to go up. What about negative x squared? We learned that already. That's a negative even function. It's basically a parabola pointing down. But what about if it's a negative odd function? Then it's a cubic function going down as well, right? Now I want to explain what the note says about how they describe it in a second by thinking it differently. I want you to think of this as the following. If this is the axis, right, for all of them, and you can think of this as being split into two left and right halves, right? On the left half for this graph, you see how it's going up on the left side, okay? And on the right side of it is also going up. You agree? So for the first picture here, for the positive even polynomial, if you look to the right side of the graph, it's pointing up. And if you look at the left side of the graph, it's also pointing up. What about for the the second one in the bottom? The odd degree is positive. Well, if you look at the right side of the graph, it's pointing up. But if you look at the left side of the graph, it's pointing down. So how do they describe that in calculus and pre-cal? This is what all this is about. It's basically saying I'm gonna basically repeat what I just said, but we're gonna use the terminology, at least the written terminology here. So here we go. What does this say here? Now it's usually backwards. I prefer doing this way. As I look to the left of the graph is going down. I rather think of it this way instead of saying the graph is going down as I look to the left. It doesn't matter the order. It really doesn't. But as long as you understand that the graph, the visual graph is f of x, right? And that's if you look to the left or right of it. So as I look to the left, and how do I know it's the left? Because it's negative infinity. So as I look to the left of the picture, the left side of it, the graph is going to start pointing down. And if I look to the right of the picture, the graph is going to point up. Now, how do I know this is to the right? That's a positive infinity. How do I know it's going up? Because it's also saying it's going positive infinity. So that's going to be this example here. If I look to the right, it's going up. If I look to the left, it's going down. That's that example. It says it right here, x to the third power. So that's how they would describe it. I want you to always keep in mind, it's not that complicated, but I don't want you guys to be too worried. It's important that you guys at least have a sense of the picture, and that's more important than anything else, okay? So let's look at example A, and we'll figure out what's asking us to list all the zeros, multiplicities, but I'm gonna just skip that for now and just worry about the end behavior. So we're not gonna do this. We're gonna do just end behavior. End behavior is simple. It's basically you have to find out what the degree is and whether it's positive or negative. That's all you got to do. So let's figure out the degree here. So we already had practice on this. So let's do that. It's pretty fun and quick and easy. So 1 times 1, this has a value of 1. 1 times 1, this has a value of 1. 1 times 2, this has a value of 2. 1 times 1, this has a value of 1. If you notice, all the x's are going to have the 1 power. So you don't have to really worry about multiplying. That's how you're going to have to do it in my class and my test, my homework. You're not going to have a situation where x is squared. So all you're really doing is just adding these powers, if you think about it. That's all you're really doing. So 1 plus 1 is 2, plus 2 is 4, plus 1 more. My degree is 5. Now, the question is this an even or odd polynomial? Well, you have to look at the coefficient at the very beginning, right there. Even though you don't see a number, we know better. We know it's a positive 1 hiding there, right? So it's going to be a positive. It's a positive odd. This is an odd number, right? The degree is odd. So it's a positive odd function, odd polynomial. A positive odd polynomial pretty much looks like this from far away. That's what it looks like. So in other words, as you look to the right of the graph, as you look to the right, the graph goes up. And as you look to the left, the graph goes down. Now, I'm okay with something like that as an answer, but this is how you would describe the answer. You guys understand? So, example 9 and 10 are asking us to, had some stuff written earlier, are asking us to find out what equation could you have for this picture you have in front of us. So I want you guys to learn just the strategy. It's really simple. We're not going to verify with the graphing utility. Just we're going to know what's the answer. The way to do it is quite simple. First one, you have to find, or at least identify, right? Identify the zeros, okay, and determine, or you can call it x-intercepts, whatever you like to call it. Oh my gosh, my handwriting. X-intercepts, and determine if bouncing, touching, or crossing. Okay, this is to determine the multiplicity. Okay, so, and then after that, you use a point, a different point. I'll say a different point. You can't use the x-intercept again, so you use a different point to solve for the coefficient. And you'll see what I mean in a moment. So the equation is always going to look something like this. Y equals to a times x minus p times x minus q, etc. That depends on the number of factors. And they're all raised to some kind of power, okay? Depending whether it bounces or crosses, right? So it's actually quite simple. So step one, let's figure out the solutions, the zeros. There are 3 solutions, 3 zeros, so I know it's going to have 3 factors. And because I don't know what the coefficient is, what this a is, I'm just going to leave it as a in front. So that's step 1. We're actually going to do step 1 for example 10 as well. Might as well do it at the same time. There's 1, 2 zeros. So we're going to do a times parentheses times parentheses, 2 factors. Now, the solution here is -3. What would the factor be for its solution to be -3? And this is an early example we did. So the factor would be x, not -3, but x plus 3. X plus 3, the solution will be -3. Okay, the solution here for this one is -1. So what factor would give me a solution of -1? Well, it would be x plus 1, because if you plug in -1 into x plus 1, you get a solution of 0. And last but not least, the solution is +2. What would the factor be? X minus 2. So that when you plug in 2, it gives you 0. And now we're going to focus on whether it crosses or bounces. So if it crossed, like for example the first one, x plus 3, it crossed, see how the graph crossed? We're going to leave this as a power of 1. It's an odd multiplicity. But for this solution of -1, it touched that point, right? It didn't actually go through it. That's an even multiplicity. We're going to use 2. Now remember, you're going to use the smallest degree for every factor. We're not going to put 200. We'll just say 2. And the same is true for the final x-intercept. At 2, it crosses. We're going to use a 1. You don't have to write 1, but I'm just doing it for the sake of the question. And now we have to figure out what a is. So we already did step 1. Step 2, to find a, we need to go back and pick any other point other than the x-intercept. You can't plug in the x-intercept, because if you did, it'll cancel everything out. So pick any other point. Technically or typically, the y-intercept, if it's not already an x-intercept, because it's not the origin, the y-intercept is a good point to use. So in this case, 0, -3 is a great point. So I'm going to use 0, -3, this coordinate. I'm going to substitute 0 into the x's, and obviously -3 into the y's, and into the y, rather, there's only one y. And then we're going to solve for a. So it looks like this. -3 equals to a times 0 plus 3, 0 plus 1 squared, 0 minus 2. that would be 3 times 1 times negative 2. I think you guys would agree that's just negative 6a. So if you divide both sides by negative 6, you're going to get a equals to positive 1/2. Once you have a, we're ready to finally put the answer 1/2 x plus 3, x plus 1 squared, x minus 2. And voila, you're done. Quite simple. We'll do this one as well. So again, the solution is 0 in this case. So you don't necessarily have to put x plus 0, x minus 0. You can just put x. And it's going through, so it's going to be a 1 power. Here at positive 1, the solution is positive 1, so the factor has to be x minus 1. And it's touching at that point. So we know it has to be an even multiplicity. We put a 2 there. And now we can't use, in this example, we can't use the y-intercept because the y-intercept is also an x-intercept. So we have to use a different point, which is why they identified a point way down there. So they want us to use 2, negative 4 into this equation to solve for a. So we're going to plug in negative 4 to the y equals a times 2 minus 1 squared, which is basically negative 4 times, this is 2 times 1, so 2a. You divide both sides by 2, you're going to get negative 2. So the final answer would be y equals to negative 2 times x minus 1 squared. And you're done. That's example 10. Now the last page is, we're not going to do both because of, boy, sorry for all this writing. I was testing this software, so okay, so the last one, we're only going to do one of them because it's already been 36 minutes. I want to make sure this video is going for an hour. So the last one, we're going to basically just answer all the questions, step 1 through step 5. So step 1, it's asking us to determine end behavior. Well, in order to determine end behavior, remember, we need to know the degree. So end behavior means what kind of picture it has, right? So we have to determine the degree. So let's find out what the degree is. The degree of this polynomial equals to, let's see, 2 plus 1 plus 1, that's 4, right? So the degree is 4. You know what? I'm going to do the end behavior, but I definitely don't want to do step 4 at that point. So we're going to do step 4 right away after we do end behavior. Step 4 is turning points. We'll do that in a moment. So the degree is 4. Now we have to determine whether it's positive or negative. We zoom in and look here at the coefficient, which we don't see a number, but we know better. We know it's a 1. It's positive. So this is a positive even polynomial. Okay? Which basically means it looks like a parabola. In other words, as x goes to the right, as you look to the right of the graph goes up. And as you look to the left of the graph goes down. That's what that means, okay? Now the number of turning points, we said a second ago, that's an easy one. I'd rather do step 4. That's just whatever the degree is minus 1, or in this case 3. That's really, really easy. Now we're going to just do step 2 and 3 at the same time, okay? So 2 plus 3. I'm not going to do the y-intercepts. I'm just going to do the x-intercepts. But as soon as I do the x-intercept, I'm going to go ahead and do the multiplicity, and if whether it crosses or touches the x-axis. So let's do this. For the first solution, factor, x plus 4, we know the solution for that is negative 4, right? Because negative 4 plus 4 is 0, obviously. The multiplicity of this particular factor is a 2, which makes it an even multiplicity, which implies it's going to touch the x-axis at that 0. The next factor, x plus 1, has a solution of negative 1. That multiplicity is negative 1. Oops, sorry, positive 1, forgive me. Multiplicity is just a number, which is an odd multiplicity, which means it crosses the x-axis. And finally, the solution for the last factor, x minus 2, is positive 2, with the same multiplicity as the prior question, or factor. It's 1, which makes it an odd multiplicity, which means it crosses the x-axis. So if you were to try to, quickly graph it, I know we don't have the actual y-intercept, but we know it's going to look like a parabola. So step 1, when you do this, you put the intercepts down. So we have negative 1, negative 2, negative 3, negative 4, and positive 2. Right? These are all oops, x-intercepts. Boom, boom, boom. Okay, so we got those intercepts. Now we know that the graph will eventually look like a parabola, so it has to go up on both sides. We know that because we did that in step 1. Now, at -4, the graph is only going to touch. So I need to make sure this turns around like that. But then eventually it has to turn again because it has to, at -1, it has to go through the graph. And then again it goes through the graph one more time at 2. So it has to go through the graph and then goes through the graph. So the graph, it's rough sketch looks something like that. Is that exactly like a parabola? Of course not. But I mean, from far away, it pretty much looks like that little parabola. And that's it. That's all there is to this lesson. I'm just going to skip the last example out of interest of time. Hopefully you guys enjoyed it. And again, leave me any comments. I'll see you guys for the next video.